Everyone, welcome once more to today's YouTube channel, Best Science Brain. Today we are still having another physics content, and today the topic on the board is energy quantization. So today we are taking a branch of modern physics. So today's tutorial is meant for students in high school, that is senior secondary 3, SS3. This is a key examination topic, and also is also good for students that are in year 1 of high institution who are doing their general physics. So students in high institution, this topic is also beneficial to you guys, either in year 1 or year 2 of those who are doing physical sciences. So today, before we go on, we'll continue with the topic. If you are not subscribed to the channel, please subscribe. If you are seeing the channel for the very first time, subscribe to the channel by tapping on the subscription bell, a tiny bell, or the icon, which you're going to find it under the profile picture or under the channel the Best Science Brain. You see a tiny bell. Tap on it once and get subscribed and follow us as we roll through the channel, dishing out lectures on chemistry, physics, further mathematics, and also practical lectures. So today we're going to energy quantization. So modern physics tells us that the electrons in the atom are placed in different energy levels. Electrons in atom are placed in different energy levels. These energy levels are shells, which you can describe with a diagram from Rutherford experiment. If the center of the atom is called the nucleus, which contains proton and neutron, that from Rutherford description or from Bohr's description. So we have the proton and neutron at the center of the atom. Then you have the shells. These shells are also called energy levels, or you can call them orbits. So this is the K shell, this is the L shell, this is M shell, and N shell, based on your knowledge in chemistry. So you understand that atoms are placed in discrete energy levels or shells. So the placement of, electrons are placed in discrete energy levels or shells. The placement of electrons in shells or energy levels is what we call energy quantization in an atom. Okay, coming down to physics, we may not start drawing the shells in this circular manner. We can have a different picture to represent what we have on the board. So the different picture, instead of drawing shells in this manner, we can remove this and then draw it in this way. So the first shell, that is horizontal line. So the first shell having energy of E0. This refers to the K shell. The E1, the next shell. So here N is 1, N is 2, N is 3, N is 4. The N is what we call the principal quantum number. So this is E2, E3, and so on. If you refer back to your knowledge of chemistry, your K shell, for the K shell, N is 1, because it's the first shell after the nucleus. For L shell, N is 2. For M shell, N is 3. For N shell, small n is 4. For O shell, small n is 5. So going to this diagram, when we write N as 1, this line represents the K shell. The second line represents the L shell. The third line represents the M shell. The fourth line, which is N equal to 4, represents the N shell, and so on. Until we reach a point where the lines are close to each other. At this point, the electron is about to leave the atom. So now I say we can have N infinity, or the infinite energy here. Now when electrons are in the atom, the electrons are not restricted to stay in a given shell. Electron can jump from a lower shell to a higher shell. For instance, if you have the proton and neutron at the nucleus, electron in the K shell can jump from K shell to L shell. It is possible, yes. Electron can also jump from K shell to M shell. So electrons can make what we call quantum jump. That is jumping from a lower energy level to a higher energy level. This occurs when electrons gain photons of energy. Photons means discrete amount of light energy. So an electron can move from K shell to L shell, or from K shell to M shell, or to even higher shells, from K to N shell, and so on. So when an electron moves from a lower energy level to a higher energy level, it undergoes what we call quantum jump or excitation. Excitation is a process by which an electron jumps from a lower shell to a higher shell. Now, how do we denote this movement or this transition? We draw a spectral line. A line showing the movement from a lower shell to a higher shell. Now let's go back to our diagram. So if an electron moves from K, this is the K shell, N as 1, to L shell, we'll draw a spectral line showing the movement or the transition pointing upwards. If an electron moves from K, maybe to L shell, we'll draw another spectral line. This is from K to L, to this is your K shell, this is your L shell, this is your M shell. If an electron moves maybe from K shell to N shell, we'll draw the spectral line from K, showing where it was and showing also where it's going to. So this is what we call excitation in physics. So excitation is a process by which an electron undergoes a quantum jump. From the word quantum means amount, undergoes a quantum jump from a lower energy level to a higher energy level. That's what we call excitation in physics. So you can see electrons are not restricted according to the old theory of atoms. Our electrons, in the ancient theory, we are told electrons are supposed to stay in the bipolar shell. No. But if you read the Niels Bohr's assumption, electrons are not restricted to stay in a shell. They can stay in a shell when they have neither absorbed nor radiated energy. But once they absorb energy, which described as photons of energy, discrete amount of energy, light energy, they can jump to a higher energy level. For instance, if the K shell, that is this EO, has an energy level of 800 joules, let's just give an instance, and this E1 has an energy level of 1200 joules, and then this E2 has 2000 joules of energy, and then this one has 3000 joules of energy. Now, for electrons to move from E0, which corresponds to the K shell, to E1, you're going to absorb the difference. 1000 minus 800, 1200 minus 800, you're going to absorb extra 400 joules of energy. For electrons to move from ground state, that is the E0, to E2, you're going to absorb the difference in energy, 2000 minus, you're going to absorb extra 1200, because 2000 minus 800 is 1200. For electrons to move from this state, the K shell, to the E3, the different energy is going to be 3000 minus this, which will give you 2400 joules of energy. So the energy difference represents the amount of energy electron will absorb to move from a lower energy level to a higher energy level. So that is excitation in physics. We need to understand this concept. It also applies in chemistry, but for today, we are talking about atomic physics. Okay, having done that, the question is this. This lowest energy level of the atom, what is it called? The lowest shell. In physics, this lowest energy level of the atom is called the ground state. The ground state. So the ground state is the lowest energy level that an electron can attain. Describe excitation as electron movement from a lower energy level to a higher energy level. When the electron absorbs radiation, it jumps to a higher level. Then, the question now is this: can electron move from a higher level to a lower energy level, then from a higher shell to a lower shell? Yes. What will happen for electron to move from a higher level to a lower level? That is when the electron has lost energy, that is radiation, due to collision with the molecules of air or environment. So electron can still lose energy and jump from a higher level to a lower level. For instance, electron can move from E3 to E0 to the ground state. Electron can still move from E2 to E0. So you see the arrow pointing downwards. That is radiation. In excitation, the arrow will be pointing upwards. It's going from lower to higher. But in radiation, when you lose energy, the arrow will be pointing downwards. See the spectral lines. Electron moving from a higher energy level to a lower energy level. Now, let us just take one spectral line for our illustration. Let's say the electron is moving from n equal to 4, which represents this is the K shell. Also in chemistry language, represent the N shell. So if the electron moving from N shell to K shell with the lower energy, so how do we calculate the energy of a radiation emitted? So energy of radiation emitted will be the difference in the two energy levels. So it's going to be the energy at E3 minus the energy at the ground state. So you can see that. So when electron emits radiation, the energy of radiation that is emitted is different between the two energy levels. For instance, if this is minus 12 electron volts, and the energy here is minus 8 electron volts, and we are told that electron jumps from E3 to E0, and you ask calculate the energy of the radiation emitted. We apply use the difference between E3 and E0, which should now be the value of our E3 is minus 8. The value of our minus of E0 is minus 12. We now have minus 8 plus 12, and that's going to give us 4 electron volts. So this is how you find the energy of electron during transition. So the energy of radiation during transition, radiation absorbed or the radiation emitted. You take the difference between the two energy levels. And energy can be expressed in electron volt or can be expressed in joules. So having done that, we now look at Planck equation. So Max Planck was able to derive the energy of radiation as E energy equal to HF. So where E stands for the energy of radiation and H is known as Planck's constant. The constant, which is equivalent to 6.626 times power minus 34 joule per second. So that is Planck constant. Approximately 6.626 times power minus 34 joule second. And F is the frequency of radiation. So the energy of radiation given by the formula Planck constant times frequency of radiation. I will know that from our knowledge of waves in physics, velocity of wave given by wavelength times frequency. Velocity of wave given by wavelength times frequency. I will know that light or electromagnetic waves have constant velocity. The velocity of electromagnetic waves begin by 3 times power 8 meter per second. So all radiations or all electromagnetic waves have the same frequency of 300 million meter per second. Now, because the frequency of radiation is constant, so we can replace this V with C, meaning constant frequency. So we can now say C equal to lambda times frequency. Now, making frequency the subject, so our frequency now becomes equal to C over lambda. So we are getting frequency expression now. So going back to this formula that says energy of radiation given by H times frequency. We can now say that energy of radiation H replace frequency with velocity over wavelength. We now have C over wavelength. So the energy of radiation, according to Planck equation given by HF or Hc over lambda, where F is the frequency of radiation, F is a constant, which we are given the value before as the Planck constant. Lambda is the wavelength, and C is the constant velocity of radiation or of light, given as 300 million meter per second. So now we're going to take some problems on this. On the board that says calculate the energy of photons of light or frequency 5 times 10 raised to power 11 kilohertz. I will have the Planck constant under it, 6.6 times power minus 34 joules second. Now to solve this problem, we are given the frequency of radiation as 5 times 10 power 11 kilohertz. We have to standardize this unit by converting it to SI unit. So how do we do that? We have this times 1,000, because 1 kilohertz is equal to 1,000 hertz. So our frequency now becomes 5 power 14 hertz. That's our frequency, adding the powers together. Then we are looking for energy. Energy of photons or radiation given by Planck's equation, which is HF. Planck constant times frequency. That gives us, the Planck constant is in bracket 6.6 power minus 34 times 5 times power 14 to get the energy of the photons. So if we multiply, it will give us 33 power minus 34 plus they give us minus 20 joules. We express our answer in SI unit. So in in standard form, it's going to be 3.3 power minus 19 joules. That becomes the energy of the photons of light. 3.3 power minus 19 joules. So you can go through our work again. To solve this problem, we need to use, since we look for the energy of light or photons of light, we need to use the Planck equation we given as E equal to HF. Before we go on to do that, we need to convert the frequency from kilohertz to hertz. 1 kilohertz is equal to 1,000 hertz. So apply this together. To join these two together, you follow the law of indices or use a calculator which says AM times AM, where you apply two indices of the same base, add their powers and take only one base. So that's what I did here. Taking one, the 10, then 11 plus 3 giving us 14. We now have the frequency there. Then you now apply the Planck equation, make a substitution, and then solve. You now get the energy of the radiation. So that is the answer. So 3.3 power minus 19 joules. Let's go to the second question over there. Number 2 says, during the transition of an electron, 1.2 electron volt energy or photons were emitted. Calculate the wavelength of the emitted radiation. During the transition of an electron, 1.2 eV energy of photons were emitted. So that 1.2 stands for energy. So the energy of the photon emitted is 1.2 electron volts. This is not yet in SI unit. We have to standardize the unit. So the SI unit of energy is joules. We ask ourselves how many electron volts, how many joules make 1 electron volt. We have the standard there. 1 electron volt equal to 1.6 power minus 19 joules. So we have to convert this to joules by multiplying 1.2 by 1.6 power minus 19. So I can bring the thing to joules. We multiply 1.2 by 1.6 power minus 19. We're going to have about 1.92 times this power minus 17 joules. So that becomes our energy. 1.92 to the power minus 17 joules. So the question says we have to calculate the wavelength of the emitted radiation. Find the wavelength of the radiation emitted. So we now remember the Planck equation that says E is equal to HF. So we're looking for wavelength. What I have to do is remember or recall from my introduction that speed of radiation given by wavelength times frequency. And then wavelength is equal to speed or velocity over frequency. So I will now replace F with C over, I made a mistake here, frequency becomes C over wavelength. We go to this equation and replace our F with C over wavelength. Now I have here's C over wavelength. So this is the energy of our radiation now. So we'll now go ahead and then calculate the value of our Planck constant given to us in brackets as 6.6 power minus 34. The value of the speed of radiation they give us as 3 to the power 8. We'll come back to this place. So the value of our H is already written there. Speed of radiation is 3 to the power 8. So what are we looking for? Looking for what? Looking for wavelength. We made a mistake here. We're looking for wavelength. Okay, before we go ahead, we are right. So before we go ahead, what we should have done is to make wavelength the subject of the formula. So if we can apply, wavelength should be equal to C over E, making well the subject before we substitute. Then we substitute now. The value of our H is 6.6 power minus 34, which is the Planck constant. Speed radiation, the one in bracket, which is 3 to the power 8. And then our energy of radiation is now 1.92 power minus 17. So when we solve this, we get our wavelength, whatever the answer is, in meters. That becomes the wavelength of the radiation. So we have the next problem on the board that says, given that an atom has the following energy levels and the corresponding values. These should be values. E0 equal to minus 12.0 eV electron volts. E1 minus 5.7 electron volts. E2 negative 2.6 electron volts. E3 0.00 electron volts. But one question says sketch the energy level diagram of the atom. So let's start with this first equation to sketch the diagram. So we have to organize the energy levels given to us. This E0 means the ground state or the lowest energy level of the atom. So to sketch it, we'll draw some horizontal lines. So this is our E0, or taking n as 1. So E0 is equal to minus 12 electron volts. The next level goes up, that n becomes 2. Then E1 becomes equal to minus 5.7 electron volts. The next level, which is this, n becomes 3. Then E2 becomes minus 2.6 electron volts. The next level, n equal to 4. Then E3 is 0. So that point being 0 means the atom is about undergoing ionization. So that is the electron level of 0, energy of 0. When you have 0, what you do is sketch lines that are close to each other, showing that the atom is about to leave the electron is about to leave the atom. So now this is the energy level diagram. That is the answer to question number I. Number 2 says draw a spectral line to show electron transition from E3 to ground state. Draw a spectral line to show transition from E3 to ground state. So this is E3 to ground state, E0. So you draw a line from E3 moving to E0. That's what they need from you. So from this question, that is number 2. A line showing the movement electron from E3 to ground state. So this is the spectral line going from E3 state to ground state. And the arrow should be pointing downwards. So number 4, 3 says determine the wavelength of radiation emitted in question 2. Find the wavelength of radiation emitted in question 2. Okay, what do we do? The first thing we have to do is we'll calculate the energy of this radiation emitted. As I told you in the introductory part of this video, that the energy of the emitted radiation is the difference between the two levels. So the energy of emission of emitted radiation now becomes the energy of E3 minus that of E0. The energy of the E3 level is 0.00 electron volts. We now have 0.00 minus energy of the ground state, where it's going to is minus 12. Minus 12. That gives you minus give you plus. That gives us 12 electron volts. So this difference in energy corresponds to the energy of the photon that is emitted or radiation emitted. But how to convert this energy to joules? How to convert 1 electron volt again by 1 to the power minus 19 joules. You can see it in bracket where they wrote EV equal to 1.6 power minus 19 joules. You convert to joules first. When we apply this, the value you're going to get is going to be 1.92 to the power minus 18 joules. So this is the energy of the emitted radiation. 1.92 to the power minus 18 joules. Then, since we're looking for wavelength of the radiation emitted, recall Planck equation that says E equal to hf. So that's our Planck equation. Energy equal to Planck constant and frequency. But we are not looking for frequency. Remember, we're looking for wavelength. And then from our small knowledge of waves, we know that velocity, which is v, but this time I'm applicating as c, is wavelength times frequency. Wavelength becomes velocity, the speed, constant speed over frequency. Bringing this into this formula, we now have E equal to Hc over frequency. Okay, we are making wavelength the subject of the formula. Let's go back to this. We are looking for wavelength. We are trying to make frequency the subject, sorry. Frequency becomes C over wavelength. So you come back to this place and replace frequency with this. We have Hc over wavelength. So you go ahead and make wavelength the subject. So our wavelength now becomes equal to E over Hc. When you cross multiply, we now have your wavelength. So wavelength now becomes the value of your E have been calculated before, which is the difference. 1.92 power minus 18. Come back this side. Then our Planck constant is 6.63, which is given to us in the bracket. That is it. Power minus 34. Then our speed of radiation, which is this constant, 3 to the power 8 meters per second. So solving this out to find our wavelength, the wavelength is going to be 3.4 times 10 to the power minus 8 meters. 3.4 to the power minus 8 meters. So this is the wavelength of the emitted radiation from this illustration. So go through our work and then see how it's being done.